Hello everyone, welcome to the NN Classroom. Today I'd like to share with you a past paper question from 2017, time zone 1, question number 12, relating to the topic 4 and 14, the SL and the high level for the bonding and structure topic. Again, a really important topic that tests for quite a lot of the points in paper 1 and also paper 2. Let's see, they're asking, which combination describes the bonding and structure in benzoic acid? So given to you the formula C6H5COOH. Obviously, the COOH pattern is one of the functional group concerning the carboxylic acid in these organic compounds, right? Yeah, although it's not the main point in this question, but just remind you. Yeah. So in this case, the technique or the first step always true is that remember we should first sketch the Lewis structure for this compound. If you are not so confirmed or not so sure about whether there will be some hidden bonds or hidden elements inside this compound or what we call the skeletal formula, better we first sketch the what we call Lewis structure. Simply applies the electron dot diagram. So in this case, we know that one corner corresponding to one carbon according to the rules of establishing a skeletal formula. So in this case, we should be having 1, 2, 3, 4, 5, 6 carbons, right? And then one outside link to a COOH group, right? And then as you need to know that within this circle, we call it a delocalization of electrons, right? And this delocalization is because of the pi system having a conjugated system. A conjugated system simply implies an alternate double, single bond pattern. So that's why, more obviously, if we are now breaking down the delocalization, we should sketch back the bonds one by one, right? In terms of having an alternation of single, double, right? And finally, count the bonds carefully. As we all know in organic chem, carbon needs 4 hands, or simply means 4 bonds, right? So that's why you can see this carbon that I'm now pointing is already having 4 lines, so 4 bonds. So okay, right? But for some carbons, they are not yet having 4 bonds, just like this carbon, right? You see only 1, 2, 3 free hands. That means one hydrogen is being omitted. So that's why this is also the characteristics of the skeletal formula, in which some of the hydrogens are being understood and so omitted, right? So that's why you need to point it back from the skeletal formula. So once this is done, so all double checking, all carbons have 4 bonds now, and then oxygen having 2 bonds, and hydrogen only have 1 bond, right? So that is obviously the true Lewis structure. And finally, put back the lone pair electron as well. Although it is not important in this time, but remember, for Lewis structure, quite a lot of students just at the end forget to put back the lone pair electrons. So remember, for oxygen, in this case, both oxygens having 2 lone pairs of electrons, right? Make sense? So in this case, we further look for it. First, the number of electron domains per carbon atom. So in this case, you can see all the carbons are actually having a free domain situation. How we count it is that one of the bonding area is talking about 1 domain. No matter double bond or triple bonds, all those count as 1 domain. So that's why we use the word domain instead of pair, right? So that's why in this case, this carbon, like this situation, there's a bonding area, 2 of the bonding areas, and also 3 of the bonding areas, in which multiple bond count as single domain. So that's obviously all having 3 domains, right? No matter this carbon or even outside the ring carbon, right? Still having 1, 2, 3 bonding areas. So that's a 3 domain in total. So again, we can Q, C, and D already, right? Next, the number of pi bonds. So do remember what is meant by pi bond, and simply understanding is that whenever there's a covalent bond, the second bond or the third bond in a double bond or in a triple bond situations, those are counted as pi bond. This is the most straightforward understanding. And sigma bond, which is always counting to be the first bond, the first interaction within a covalent manner or covalent bond, must be in a sigma fashion. Yeah, then you need to know the reason behind and what is meant by sigma and pi further. That is talking about the molecular geometry or the overlapping geometry between the 2 orbitals. Yeah, but this is something that later on that you should know within the textbook. Yeah, but let's see, within this technique, we should notice that the pi bond is talking about the second or the third bond if there is going to be any. So just like this case, we can see some second bond, right? Just like here, we see 1, 2, 3, within the ring, and then 1 also outside the ring. So altogether 1, 2, 3, 4. 4 pi bonds, implying that 1 bond, 2 electrons, right? So 4 pi bonds, 8 pi electrons. 8 pi electrons, right? So further double check for the sigma bond, which is going to be the first bond. How many first bond do we have? I use a red color to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Yeah, so all together we have 15 pi bonds, right? As 15 sigma bonds, sigma bonds, right? So sigma bonds, the first bond, which is going to be 15, and this time they're asking for bonds, right? So that's why we no need to multiply by 2 in counting the electrons, right? So simply means 15 sigma bonds, right? But 4 pi bonds, so 4 pi bonds, 8 of the pi electrons, right? So that's why the combination that is going to be correct, B.